We are now going to perform analysis of BJT circuits to which only DC voltages are applied. We will assume VBE to be 0.7 volts and VCE SAT to be 0.2 volts. However, a fundamental question has to be answered. Which mode is the BJT operating in? Fortunately, we have a series of steps that can guide you. Firstly, assume that the transistor is in active mode. Make all the calculations that you are asked to do. Then check for consistency of the results with the assumption of active mode operation. That is, VCB is greater than minus 0.4 or not. That is for NPN. For PNP, the situation is reversed and VCB should be lesser than minus 0.4. Now, if the answer is yes, then your assumption was correct. However, if your answer was no, then assume saturation mode. Carry out the calculations and check for consistency with the assumption of saturation mode. Now here the test is a bit different. Here you have to check whether the forced beta is lesser than the beta in the active mode. However, beta for a given transistor varies over a wide range, so one should use the lowest specified beta for this test. Now that we have gone through these conditions, let's start with our circuits. Here we are. There is your familiar common emitter configuration. You are given beta as 100 and your task is to find all node voltages and branch currents. So, remembering our first step, we are going to assume that this is in active mode. We can write a value for the emitter voltage, 3.3 volts. Similarly, we can calculate the current IE, 1 milliampere. Now, since beta is given, we can calculate the value of IC. This is 0.99 milliampere, and using that we can calculate VC. This comes out to be 5.3 volts. So, it is time to check our assumption. VCB equals VC minus VB is 5.3 minus 4 and equals to 1.3, which is greater than minus 0.4. So assumption was correct and this is indeed in the active mode. Similarly, we can find the base current. Take a look at this formula. IB is equal to IE divided by beta plus 1. This will give us IB equals to 0.01 milliampere. Now remember that this hand analysis is only done so that you can get deeper insight into the circuit. Much quicker way to get all these values is simulate this using a software, but that is not going to give you the insight that handwritten analysis gives you. So, in order to save your time, you need to make all these calculations and complete your analysis in a very short span of time. So, it is essential that you practice a lot so that you spend less time getting confused over the equations and spend more time in your calculations. Now let's make a modification to this. Let's put VB at 6 volts. Again, our task is to find all the node voltages and branch currents. So we are going to erase all this and start again. We can again write the equation for VE and IE. Using IE, we calculate IC, 1.58 milliamperes, and using that we can calculate VC, 2.48 volts. So, we are going to check our assumption. VC minus VB, 2.48 minus 6 equals minus 3.52 volts, which is less than minus 0.4 volts. So, our assumption that the transistor is operating in the active mode is incorrect. So we move on to the next step and assume that the transistor is in saturation mode. Now, which of these equations should we keep? The first one, VE equals 6 minus 0.7 equals 5.3 volts, is not affected by this. So that one is going to stay. Similarly, IE is also going to have a value 1.6 milliampere in saturation. However, the beta has now changed, so we cannot use the equation for IC, and similarly we cannot plug in that value of IC into VC, so we have to recalculate them. Now remember, VC equals VE plus VCE sat. This is simply the definition of VCE, which is VC minus VE. So we know VCE sat to be 0.2 and we calculate VC as 5.5 volts. Now I have a question for you. Why did we assume VE and IE to be the same? Remember, in saturation mode and also in active mode, the emitter base junction is forward biased. It is only the collector base junction that has a different biasing in saturation and active mode. That's why VE and IE are the same. So let's calculate IC, 0.96 milliampere, and this is quite different from the IC that we had previously. Using this we can calculate IB, 0.64 milliamperes, and notice that we have used Kirchhoff's current law for the transistor that we had done in one of the previous lessons. Basically, current entering the transistor should be equal to current leaving the transistor. So, IB is calculated and we need to find beta first, 1.5. And indeed, it is less than 100. So, our assumption that the transistor was in saturation is correct. Now let's make one more change, and this will be the final change. Let's ground VB. What will happen now? Now remember, in both active and saturation mode, the emitter base junction was forward biased. This meant that the base was at a higher voltage than the emitter. However, in this case, we can see that both the emitter and the base are grounded. So in this case, the emitter base junction cannot conduct. Similarly, in the collector base junction, the collector base junction cannot conduct since the N-type collector is connected through RC to the positive power supply while the P-type base is at ground. Therefore, the collector current will be 0. So, the transistor is in cutoff. The emitter voltage will obviously be 0 because no current is flowing, and the collector voltage will be equal to 10 volts. Straightforward, yes? Now it's time for our quiz.